Hey guys, in this video we are going to be switching gears a little bit within our solutions unit. We're going to talk a little bit more about acids, bases, and salts. First off, let's look at properties of acids and bases. So with acids, acidic compounds give foods a tart or sour taste. So imagine if you're eating something that has any type of vinegar, lemon, or citric acid like juices and sodas. You kind of have that tart aftertaste. Acids are going to cause a color change when combined with chemical indicators. Indicators that we're most familiar with are going to be the litmus paper, the little pH strips. With acids, they tend to turn red. We also have a chemical indicator we use called phenolphthalein. This a lot of times they'll use to test for blood and stuff like that. Whenever it's mixed with acids, it is actually clear. So you're looking for with indicators, litmus paper is going to be red with acids, and phenolphthalein will be clear. Acids act as electrolytes and can actually conduct electricity, so they separate into ions that will conduct electricity. Um, and you may have heard of electrolytes with Gatorade and stuff like that. Gatorade has those dissolved salts in it to kind of replenish stuff in your body after exercising. That will actually also conduct electricity because of all those dissolved ions. And whenever acids mix with compounds containing hydroxide, so bases, they're going to end up making water and some form of ionic salt. Let's switch over to bases. Bases have more of a bitter taste. So you may think of milk as slightly basic. It can have a bitter taste to it. Most bases are actually hazardous to taste. A lot of our bases are going to be stuff like soap, bleach, any type of cleaner that you may use is going to be a base. So you may not have a lot of taste associations with these because you're not supposed to taste them. Bases have a slippery feel. So imagine if you've ever washed dishes or if you've ever cleaned the bathroom and you kind of have that slippery film or greasy film on your hands afterwards. That's from the basic soap. Bases also produce a color change with those chemical indicators, but the pH strips, the litmus paper, are going to turn more of a green or blue color with bases, whereas the phenolphthalein actually turns a hot pink color. So like I said, you may have seen this in crime shows whenever they're testing for blood. If they believe blood is there, they'll spray phenolphthalein on it, and it will actually appear as pink whenever they're testing for it. And whenever a base reacts with an acid, it will produce water and then some sort of ionic salt. So that was listed the same on the previous page. Now we're actually going to talk about the different types of acids and bases. We've talked about acids and bases in the past, as acids start with hydrogen and bases have hydroxide. That is our basic Arrhenius acid and base definition. So this is what we normally think of as acids and bases. So Arrhenius stated that acids are hydrogen-containing compounds that ionize to yield hydrogen ions, and bases are compounds that ionize to yield hydroxide. So Arrhenius said that acids produce hydrogens, bases produce hydroxides. This is our normal acid-base definition, so nothing new. So Arrhenius acids, we actually state if they're monoprotic, diprotic, or triprotic. So this just looks at how many ionizable hydrogens the acid will have. Mono means one, so monoprotic acids have one ionizable hydrogen, something like nitric acid with only one hydrogen. Diprotic acids have two ionizable hydrogens, so something like sulfuric acid. And then triprotic acids have 3 ionizable hydrogens, like in phosphoric acid. Now note that not all compounds that have hydrogen are acids, and not all hydrogens in an acid can be released as ions. Um, so we did talk about the substance must start with hydrogen. Um, so here we have like calcium hydride, which is a possibility that can form. It does not start with hydrogen, so that hydrogen is not ionizable. You might also have something like acetic acid or vinegar, where even though it has a total of 4 hydrogens, the 3 are in acetate. So the only one that's ionizable is that first one. And generally, only hydrogens in very polar bonds are ionizable. So the hydrogen needs to be attached to something relatively electronegative. All right, our second type of acid and base that we're going to come across, and this is a new definition for you guys, are Bronsted-Lowry acids and bases. Bronsted-Lowry theory defines an acid as a hydrogen ion donor, so still something that gives up a hydrogen. However, for bases, bases are the hydrogen ion acceptors. So that acid simply that hydrogen simply transfers from the acid onto the base. So this allows us to have more bases than the Arrhenius definition because our base does not have to have hydroxide in it. So we're going to look at how this works. So here we have a sample reaction, and this allows for more bases. So something like ammonia can act as a base. So if you notice here, we tend to look at how things pair up. So ammonia, the NH3, on the product side, it becomes NH4. So if you notice, it added a hydrogen from the reactant side to the product side. So this is actually acting as our base because it is accepting that hydrogen. Whereas water here is going from water to hydroxide. So it is losing a hydrogen from the reactant side to the product side. So it is acting as our acid in this case. So this is how you notice that something, even though it does not have hydroxide, can act as a base in a reaction. With Bronsted-Lowry acids and bases, we also have to label our products. And our products are going to be considered conjugate acids and conjugate bases. So conjugate acid is the particle formed after the base gains a hydrogen ion. So it goes from being a base, let me see if my pen's lined up, to being a conjugate acid. Oh, excuse me, my pen stopped writing. I'm not sure what happened. There we go. Well, it's going to be the conjugate acid. I'm not sure why it stopped writing over here. There we go. There we go. So it goes from being the base on the reactant side to the conjugate acid on the product side. Whereas our conjugate base is the particle that remains after the acid donated the hydrogen ion. So it goes from being an acid to the conjugate base. Sorry, my pen's not fully writing with me today. So here we call these our conjugate acid-base pairs. So these consist of 2 substances related by the loss or gain of a single hydrogen. So it's pairing up the base that becomes the conjugate acid or the acid that becomes the conjugate base. And note that it is not going to be an acid on both sides or a base on both sides. So it will flip back and forth. I'm going to pull up our previous reaction so you can see how these pair together. So we said that the ammonia becomes ammonium. We said since it gains a hydrogen, it is acting as our base. Well, its partner, the ammonium, is going to be our conjugate acid. So after the base has added that hydrogen. We said water was acting as our acid and becoming hydroxide, which is going to be our conjugate base. We can also do this with a whole series of other reactions as well. So for example, we might have HCN and let's do F negative producing HF and CN negative. So if we have that reaction, we'd want to pair up and see what's our acid base conjugate base. So the HCN becomes the CN negative. So it's losing a hydrogen from the reactant side to the product side. So this is our acid and it becomes our conjugate base. I'm just going to abbreviate it CB. Whereas the fluoride and the hydrofluoric pair together. So it added a hydrogen from one side to the other. Therefore, it is going to be our base and becomes our conjugate acid if we were labeling these out. All right, and then here we're going to talk about water a little bit. So water molecule, we already showed that it can lose a hydrogen to become hydroxide. But water molecule can also gain a hydrogen ion and actually become a positively charged ion called hydronium. So you may see this written as H3O+. So water is what we call amphoteric. So water can act as both an acid and a base, allowing it to be amphoteric. So anything that can be an acid and a base, so it can lose a hydrogen or gain a hydrogen, we refer to as amphoteric. Our last type of acid and base that we're going to deal with are Lewis acids and bases. So Lewis proposed that a base is going to donate a pair of electrons during a reaction, and the acid will accept a pair of electrons during a reaction. These you do not need to be able to identify, but simply know the reactions for these. And in both cases, whenever it accepts or donates a pair of electrons, it is going to be forming a covalent bond. So here's a chart that simply kind of summarizes all three types of acids and bases together. So remember, Arrhenius was our basic acid-base definition, where acids produce hydrogen, bases produce hydroxide. Our Bronsted-Lowry acids and bases were ones that we had to identify the conjugate acids and bases. So remember, the acid donates the hydrogen, the base accepts the hydrogen. Whereas Lewis focused on the electron pairs, and these tend to be opposite of what we normally think of. The acid is accepting the electron pair, whereas acids are normally the donors, and bases are donating that electron pair. And that is actually where we are stopping today. Make sure to complete the practice on the properties and types of acids and bases.